Okay, so today what we're talking about, guys, that's not the right slide. That's not the right slide. Alright, guys, today what we're talking about is what happens anytime light hits a border. Okay, what I mean by a border is, let's say light is not, let's say light's traveling in air and it hits some water. Okay, so what happens when light goes to a new medium, or not just light anyway? Okay, what happens when a wave goes from one medium to another? Okay, and then it's either going to reflect, refract, diffract, or absorb. And there are a lot of similar ones. Okay, so the first one is reflect. Anytime you look in a mirror, guys, you know that you're looking at a reflection. Okay, and your reflection is just caused by light bouncing back. Okay, so I mean the way we see anything is by light bouncing off of it. So I mean if I'm seeing you, it's because light is bouncing off of you and coming to my eyes. And so if you're seeing a reflection, it's because light is bouncing off of a mirror and coming back, right? Okay, it does that in the same way. It's very similar to an echo. Can I go forward? Yeah. This slide isn't all that important if you don't have it written. Okay. Same thing that happens in my pointer's not working. Piece of junk. Give me a second, guys. I'm sorry. Got about a what? Okay, so similar thing happens, guys, anytime there's an echo. Okay, anytime you're hearing an echo, you know that sound left and went and bounced off something and came back, right? So really, anytime you're hearing an echo, you're hearing something that happened in the past, right? I mean, because if I made a sound, I mean, I'm not making that sound twice, right? Right. I mean, you get the picture. I mean, I'm hearing something that already happened. Okay, so the same thing is true with light. Okay, anytime you're seeing a reflection, you're seeing something that. If you're hearing an echo, you're hearing something that happened in the past. If you're seeing a reflection, you are seeing something that happened in the past. Okay, really, every time you see anything, you're seeing something that happened in the past, technically. But an echo specifically, or a reflection specifically, you're seeing something that happened in the past. Okay, and that's because light does take time to travel. So if you had a super high-speed camera and you were filming yourself in front of a mirror, you would see yourself you would see your reflection just a little bit behind yourself. Okay?
Like you take a picture, and then you like see.
If you, let's say somebody was sitting here doing loosey-goosey or whatever in front of the mirror, and you were behind them recording them with like a ridiculously high-speed camera, I mean like really high speed, I mean like several million frames per second kind of camera, then you would see the reflection slightly behind the person. Okay? Make sense?
Do they have anything like that?
They do, actually. MIT has one, and I'll show y'all eventually. They have a video. It shows a beam of light moving. We'll eventually. I'll get to that.
Did you say that's how like they take the picture, like they slow it down?
Mm-hmm. Yeah. But you don't have to be that quick. I mean, it's like 3,000 frames per second instead of 3 million.
Well, if you take a picture, you know how it's like, go, like forward, like you take a picture of somebody that's like forward, is that the same thing or is it just a bad camera?
What do you mean? Are you talking about they look blurry?
Yeah.
That's just bad. Yeah, that's just a bad camera. Yeah. Okay. I don't know, I'm going to talk about that. All right, so Anytime you're having a reflection, guys, you're going to have two waves. You have the wave that goes into the reflection and the wave that comes out of the reflection. Okay, the wave that goes into the reflection, in this case it's the light coming from the flashlight going into the mirror. Okay, that is called the incident beam. The incident beam. Alright, so in terms of you standing in front of the mirror, the incident beam would be the light that comes from
Wherever your light source was.
your face or whatever and goes to the mirror. That would be the incident beam. Okay, the beam that you see, the beam that comes back, is called the beam. It's called the reflected beam. Okay, so I have the incident beam, that's the original one, and I have the reflected beam, that's the one that that's getting reflected. Okay, so in terms of you standing in front of a mirror, your face going to the mirror, that'd be the incident beam, and then what you are seeing is the reflected beam.
Why when you have a laser and you point it in the mirror, you can see on the mirror the little laser, and when you put that little laser on top of the reflection, the laser in your hand, and it points at your eye. You know what I'm talking about?
Ah, okay. That's actually a really good question. Yeah, so one pointed at mine. So you're saying when you point the beam at the mirror, it doesn't always point in your eye.
Every time I do it,
I'll show you in a second. I'm going to show you something. All right, so what we're going to end up with, guys, is two angles. Okay, we're going to have the angle of incidence. Okay, the angle of incidence is this one right here. Okay, it's the angle that that beam comes in at, and the angle of reflection. Okay, the angle of incidence always equals the angle of reflection. Okay, so if it comes in at 54 degrees, it's going to go out at 54 degrees.
Hey,
Mm-hmm.
will you put it the white one or the yellow?
This right here, where it says I, that's the angle of incidence, and this is the angle of reflection. Those are equal. Alright, so to demonstrate that, I'll come back to this. You don't have it yet. To demonstrate that, guys, I have a little mirror in there. You can kind of see it. You see the little white mirror in there? Okay. When I shine the laser into the onto the mirror, okay, what we see is that that beam is being reflected. You notice how the angle that it's coming out at is equal to the angle it goes in at? Okay. As I decrease the angle that it comes in at, you notice how the angle that it goes out at decreases as well. Okay, those are always equal. Okay, and as I increase it, then the other one increases. Okay, they're always equal. Okay, so angle of incidence equals the angle of reflection. Okay?
What's the green stuff?
What now?
What's the green stuff?
Just food coloring. It just helps you see the image a little. It helps you see the beam a little bit better.
Here I am.
Who?
For sure.
I'm right here.
Oh. All right, so reflection. Reflection, if you notice, does it enter the new medium? With reflection, does it enter the new medium? No, it just bounces off, right? So it's going through the water, hit the mirror, bounced off the mirror. That's reflection. It doesn't enter the new medium. Okay, so the next one talks about when it does enter the new medium. Okay, so when it does enter the new medium, we're going to have refraction. So reflection and refraction. Okay, so anytime a wave enters a new medium, so for example, if it goes from water to air or from air to water, okay, it changed mediums. Okay, anytime it changes mediums, then it's going to change speeds. And if the wave is traveling at an angle, then when it changes speeds, it tends to bend. Okay, so think of this as a wave, let's say a beam of light's traveling north, and then it goes into another medium, and now it's going northeast. Okay, so it can change directions as it changes mediums. Okay, so that when it changes mediums, it changes speeds, and if it changes speeds, it's going to bend. Okay, that is called refraction, guys. Guys, I'm sorry we're running. My last couple classes we've run out of time, so I'm trying to move quickly.
I thought we already did refraction.
No, that is called refraction. When reflection is when it bounces off. Refraction, okay, is the bending of light or the bending of a wave that is caused by a change in speed.
So we just wrote this.
Yeah.
So
Huh?
it's the same thing.
Same thing as the last slide?
Yeah.
Yeah. Very similar.
Literally, when you see a falling star, it actually happened 500 years ago.
Not a falling star. If you're talking about like a supernova, you mean? Exploding star?
Yeah.
It could have had. It could be more than 500 years. It could be 1,000 years. It could be 2 years. It could be any number of years.
I thought we already did the definition of refraction.
Kinda, we did. All right. So notice, guys, when it goes in at a straight angle, okay. Let me come up over here. Okay, when it's going straight in. Why is it so bright? Okay, when it's going straight in, it doesn't bend. However, if I take the angle and I tilt it, why is it? Okay, if I take the angle and I tilt it, okay, then what you see is that light bends. Okay, so here it's going straight. As I move it, you see how that light is bending? You see it right there bending?
No. It's
Oh.
bright. I can't even see.
Are you talking about like above it? That little circle? No, that's not reflection.
You see it bent?
No.
Now, I'm not saying the line's going to be bent. I'm saying it goes straight this way and then it goes straight that way. Okay? See how it's bent?
Oh, you're talking about the corner thing.
Okay, so it should... What I'm saying is if this is the surface of the bowl, okay, my light beam is coming in right here and it's traveling like that. Okay?
That's not.
Okay, so here... Okay, y'all see, can y'all see that now?
I just have one question. Are you talking about the glare?
Can y'all see that now? Let me give y'all a different angle. Okay. Okay, so from the side here. Okay. I need this little. Okay. Notice when I come, when it goes straight in, it doesn't bend at all. But as I start to angle it, we should start to see it bending. So you see that?
Oh, I see it.
You see it bent now?
Yeah.
Okay.
So it started bending when you take a different angle.
When you go to a different angle, it's going to bend. Okay, I have some other things to show y'all. Where's my little changer? Here it is. Okay, so general rule, guys. If the beam slows down, if the beam slows down, it's gonna. It's called bending toward the normal. Okay, so the normal line is going to be the line that's perpendicular to the surface. Here's my surface. Okay, notice the. Let me see if I can get the annotation up here.
What were you saying, like, if the beam slows down?
What now?
What were you saying? You said if the beam slows down.
Oh Lord, what have I done?
It's called bending toward the normal.
Oh, okay. If the beam, it's right here. Okay, so here's the normal line. The normal line is always 90 degrees to the surface. When the light beam slows down, it bends toward the normal. Okay, so here this light beam should go straight. Okay, however, since light slows down when it hits the water, see how it makes it bend toward the normal. And so that light beam is going to bend like that.
How is that normal?
The normal is, anytime you hear of a normal line, the normal line is always perpendicular to the surface. So here's my surface here. So the normal line is perpendicular to that. Okay, the opposite rule, guys, if it speeds up, it bends away from the normal. So slows down, bends toward the normal. Speeds up, bends away.
And this is refraction.
This is refraction. Okay, so notice here, it's moving straight. If it was going to go straight, it would follow the blue. Okay, but since it's speeding up when it hits air, it bends away from the normal. When I say speeds up, I mean that light moves at a certain speed in water and it moves faster in air. So it's literally speeding up. As in, like, in your car hitting the accelerator, kind of speeding up. Okay, so to demonstrate reflection, or refraction, excuse me. When they slow down, they bend toward the normal. When they speed up, they bend away from the normal. All right, so let me give you all a little example of that. Why is it doing that? Why is it doing that? I don't like that. Did I change? I must have changed some sort of setting. Let's see. Is that better?
Oh, I put it in.
All right. Anyway, so see, since this is hitting, this is the normal, this is the surface, so the normal would be here at 90 degrees. Since it's hitting at 90 degrees, there's no bending. However, guys, as I take that surface and switch it, it's going to move that normal line. Okay, so when I move the normal line, okay, it causes a bending of that light.
So how
What now? I don't know why it's doing that. It's wigging out.
So tight.
It shouldn't be flashing like that. It's flashing like that because it's picking up the light from this. Okay, so you see that's bending the light. As I take the normal and move it and adjust it, it adjusts how much it bends the light. I'm gonna see if I can.
Are you talking about the bending on the left or the right?
See, when you say it's from under it, it's
Is that okay now?
It's from the board.
Okay, well, here we go. We're good now. So let's examine this, guys. If this is the surface, then the normal line would be perpendicular. Okay, so light is going to speed, or is going to slow down when it hits glass. So if it slows down, it bends toward the normal. Okay, so it should be going, it should be going this way. If that light beam is traveling straight, it'd go right here. But you see, since it slows down, it bends toward the normal. Y'all see that?
Where is the normal?
This is the normal line. It's at 90 degrees. It's always perpendicular to the surface. Uh-huh. No, the normal would be the paperclip. The normal is perpendicular. Y'all listen up. The normal line is perpendicular to the surface. So if this is the surface, the normal line is perpendicular to it.
So it would be like the lines. Okay, these are the normal lines, and it would be these going this way.
No, this is the normal line.
Okay.
This light beam should travel straight, but it doesn't, because when it changes mediums, it bends toward the normal line. So you see it bending toward the normal line there.
So which part is the 90 part?
What do you mean the 90 part?
You said the normal line equals 90, so how did you know?
Okay, this is perpendicular to the surface. So that's not perpendicular to the surface. That's perpendicular to the surface. Yeah, look. This is the surface right here. So perpendicular to the surface would be this line right here. That's perpendicular to the surface. Okay, well now it crosses. Okay, on the other side, okay, here's the normal line, right? It should continue on through here, okay, but since it's speeding up, it bends away from the normal line. So see here, I slow down, I bend toward the normal. Here I speed up, I bend away from the normal. Light, I just know that light slows down when it hits glass. I don't like that. Alright, that makes sense? Let me show you all another one. What do you think is going to happen, guys, if I take that normal line and I bend it? Okay, so I'm going to use a curved shape now. Okay, when I take it and I use a curved shape, okay, what we see is since that normal line is constantly adjusting, guys, then that ends up giving me that. You see how they come together. Uh-huh. If you turn it around,
Yeah.
same thing. Okay, that makes sense, guys? Alright.
So what is it called? Just a hand piece of glass?
What now?
What is it called? Like,
What is what called?
Yeah.
We'll get that. It's a lens, but we'll get to it later. Yeah, we haven't covered lenses and things yet.
Does that have anything to do with the laser in the mirror?
With what now?
The laser in the mirror?
That's just reflection. The laser in the mirror. Alright, so let's kind of summarize here, guys. With reflection, okay, does it enter the new medium? No. With refraction, it enters the new medium and it causes it to distort or bend or whatever. Okay, so refraction is what is going to explain why some objects look weird when they're underwater. Okay, so for example, if you're at the side of a pool, sometimes somebody might look real short when they're not, or like the pool might not look very deep, but it's actually pretty deep. Okay, and that's because of refraction. Okay, so when the light from his foot, when the light from his foot goes up to the surface, refraction happens and it bends that light. Okay, so this light's going to come up, it's going to bend away from the normal, and it's going to go up to this girl's eye. Okay, humans can't see bending light. Okay, so any light that hits your eye, you always assume that it's straight. Okay, you can't see that it was bent before. Okay, so what she sees is instead of seeing this bent light, she sees it just as a straight beam. Okay, so instead of seeing his foot down here, she sees his foot up here. Eh? Okay, so another example of that would be here. Let me get this light turned on. Auto tune, where is it? Oh, right here. Alright, so this the staples. Okay, when you see the staples out of the water, no distortion of the staples, right? Okay. However, when the staples enter the water, oh darn it. Okay. However, when the staples enter the water, guys, do you see how they look wider? Huh? Actually, I need to pause it on here too, because I'm trying to get the video. Okay. However, when it, like I was saying, when it goes into there, what we see is that distortion there. Okay. Okay, that is caused by the refraction of light. Are the staples getting wider? No. If you were underwater with the staples, would you see them as wider? No. The refraction of light happens when they exit the water, or when the light exits the water and comes to you, because that light ends up getting bent or distorted. Okay? So, essentially what's happening here, guys, is I'm going to draw the edge of this. Okay? If this is the edge of the beaker, okay? If I have my staples coming in, okay, from outside of the beaker, the light comes straight to you. Okay? So you don't see any bending there. Okay, however, from inside of the beaker, that light gets bent. However, can we see bent light? No. So what you see is staples that are like this. Do you see that? So above, we see this. Below, we see this. Okay, and that's caused by the refraction of light. Once again, outside we see that refraction. Inside of the water, we wouldn't. In fact, inside of the water, when we looked and we saw the staples outside of the water, they look smaller, right? Be the opposite. Okay? Any questions about reflection, refraction? We have one more, but we're just going to wait and cover it on Monday. All right. Well, we are done.